All right. Last video we went over bubble sort. We went over how to create the timers and stuff to see how long it takes for things to happen. Today we're going to add, since we got all the preliminary stuff out the way, a few more sorts. We're going to see insertion, selection, and shell. And I may show you one other thing. But now all these algorithms are a little different. Notice insertion sort. We take a quick look. We've still got two for loops. We got a swap. So take a quick look at how this functions. We go to bubble sort. It goes and finds the smallest one, moves it up, and you see it's swapping all the way up. It keeps it does, if we actually did a little calculation, every time it made a swap in my code and I counted that, you would see like it could be tens of thousands of millions of swaps. Now insertion sort does it a little different. Instead of going to the bottom or finding the smallest one and varying it up, it starts swapping. Well, let's just say it takes the first couple of items, swaps them around. Takes the second couple of items, swaps them around. Takes the third couple of items. It just gradually the list gets bigger and bigger, and it's swapping the entire list as it grows. So take a quick look. You see that as the list gets bigger, it starts putting everything in order. It adds one more to the list, and then it sorts it again. Adds one more to the list, and then sorts it again. If it's nearly sorted, this is fantastic because you see how quickly it goes through that. If it's not, it takes a good bit more time. Now, selection sort is the other sort. You'll see again there's two for loops. A couple of slight differences here and how they handle a couple of things, but let's take a look. Dot, 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 dot. So if you're noticing, pretty much all of these go the same speed. Now, logarithmic time will tell you how fast something is compared to other things. So it doesn't really seem to care what order everything's in for the most part. They all tend to finish exactly the same. How many swaps? I'll have a little picture, I believe, later. Let's see, do I happen to have that picture up now, actually? I might be able to go ahead and show it to you. Let's see. I do not, but I'll have that picture up for you later in my class. Could have sworn I had that, but actually no, let's just go ahead and show it. Data structures log in, log time. Let's see, there we go, big O complexity, that's what it's called. There we go. Big O complexity basically tells you how fast a algorithm is. So if we were to take a look at bubble sort, for example, notice we go down here and we see it is adaptive O of n. We go back to my whatchamacallit and we have n, but that's only for some parts of it. You notice it's n squared when we come into comparisons and swaps. It does a lot of swaps. If we go to insertion sort, it's roughly the same because they're both loop sorts. If we go to selection sort, bubble sort, shell sort, though, take a look at this. O n 3 divided by 2, and notice that it is n log n when we go through this. N log n would be somewhere right here, I guess. Actually, no, I'm sorry. N log n is actually up here. Take a quick look at that. Shell sort. Ah, that is not what I wanted to do. Get back over there. There we go. Shell sort is n log n when nearly sorted. Now bubble sort is n squared. So n squared is here actually. Zoop. N log n is here. So you see how basically with bubble sort, selection sort, the bigger the array gets, the sharper it comes up, meaning it's horrible. It takes longer. Uh, shell sort's probably the best loop sort, honestly. Now, once we get to some of the recursive sorts, they're actually down in this range. They're so much faster, it's not even funny. So there we go. So we've got n squared, worst case, best case, depending on how big it is. N squared, pretty much all of these. Whereas this is actually not n squared. Significantly lower most of the time, definitely faster than the others. And you'll see that here in just a minute. So let's take a quick look at shell sort. Since we've already looked at the others, I think, bubble sort we know, selection sort. You'll see it just kind of goes through the entire list and finds what needs to go in that spot. Goes through the whole list, finds what goes in that spot, and swaps it. So it actually does a lot less in the way of swaps, but it does a lot. It's basically the same comparisons as bubble sort and the others. Comparisons is this bigger? Is this bigger? It goes through the entire list basically. So shell sort, on the other hand, take a look. Let's try that one more time. Now, what it's going to do is essentially split it up into parts, and it's going to sort a few things into each part. So watch this. It basically finds the ones that need to go in the top 5, puts the ones in there, but they're not necessarily in order. The second 5 puts them in there. Third 5 puts them in there. So it's actually mostly sorted after it makes that pass, which is why this is so much faster than the others. So let's take a look at them side by side if you want a good example here. Watch insertion, selection, bubble, shell, and tell me which one finishes first. Shell's done. The others are still going in some of these other cases here. Insertion and selection, bubble, there we go. Now you may have noticed that merge, quick, and these others here finished, faster than pretty much everything for the most part, except for that one exception. But these are the recursive sorts. So they're typically going to be faster, especially when we get to the bigger arrays. The bigger arrays, you notice a huge difference. Shell sort, though, is actually probably one of the best honest loop sorts. It doesn't take much effort to throw together a shell sort, but it still finishes pretty close to on par with these other guys, whereas, yeah, you see those guys take forever. So let's take a look at the actual code. Now, I've got the same program we had last time, and here's the link to that if you want to see the sorting algorithms. I think that's correct, unless they've changed it. Nope, that's right. All right. So we have our fill, same as last time. We have our print, same as last time. And I have my bubble sort here as well. Now we're going to add a couple more sorts. Now in my main, I still have basically the same code, the timer, and I'm going to do these one at a time so we can see everything. I've just got a couple other little comments in here, but we're going to do bubble sort, insertion, selection. Well, I didn't have selection there for some odd reason, but let's go ahead and add it. Selection sort. We'll see each of these in turn. We won't get too crazy with it, though. Shell sort 2. Because there's actually more than one shell sort. If you take a look over here. Well, they used to show another shell sort. There's actually some slight variations of the others, but let's take a look at our good old bubble we had last time. Insertion, we'll start with that. This is the code for insertion sort. So, post static void insertion sort, we pass it the array. It has a temp, you'll notice it's pretty similar to bubble sort. It's still got 4 loops. We do a little swap comparison. There is a slight difference, though, you'll note here. While j is greater than 0, so instead of just going this way, we're kind of going in a different direction with it. So this is insertion sort. So let's get a time for bubble, and then let's just run insertion, and we'll see how that runs. So this is it. Hopefully you got it all written down. I'll scroll on down, and I'm going to run up bubble. We'll go for 10,000. That's a good timer. I'll run it. 119 milliseconds. Okay. Comment that out. Insertion sort. 48 milliseconds. Insertion sort, particularly for that, is way faster than bubble. I wonder if we went up a little bit more to 100,000, if that would be the case. Let's see. 100,000. Yep, because 100,000 for bubble was about 12 seconds. So it is a lot faster than bubble. Still ridiculously slow, but we'll drop it back down. To do 1,000, 2 milliseconds. Okay. Now, that's insertion. Let's take a look at selection. Doop. Now you notice there's a bit difference here. We still have 2 loops, but we are doing a little bit differently here. We've got this index, we've got this swap here. So there's a couple of other things going on here. We have actually a couple of index settings. So let's take a look at how this works. All right, we got our 4, index I. That's just to save that number for later. We go in, we're comparing the current thing to the previous thing, and then we're swapping the index value. And then we do the swap at the end after this if statement's over. This is still inside the loop. So let's see how selection sort fares compared to the other 2. We've got 10,000, 57 milliseconds, 100,000, and I am filling and sorting. I think this was 4 seconds in selection, 12 in bubble, about 5 in this, and we're not going any bigger than that, I'm afraid. All right. So let's take a look at Shellsort. So selection, Shellsort. Now you'll see there's quite a few differences here. There's even some code you probably haven't really seen before in what they're doing. Basically, when we're doing this is we're doing a comparison. If it is this or that. This is basically a built-in if statement, I guess you can say. And if it's, I think if the gap is 2, it's going to use 1, or it's going to do this formula here, basically. So we still have 2 for loops, and there's a third actually in here that swaps a couple things around. And watch the, as I said before, what this basically does is it will take all the numbers and put them in their appropriate sections, although they're not completely sorted yet. And then it'll go through the entire thing and sort it at the end. And, well, if we watch all the videos, you'll notice nearly sorted always sorts faster. So Shellsort, if I go down here and check it at 10,000, 5 milliseconds. 100,000, 10 milliseconds. If you recall, bubble sort was 12,000. The other 2 were about 5,000. If I just went ahead and added 1,000,000, why not? 67 milliseconds. Shellsort is significantly faster. Now Shellsort 2, if I'm not mistaken, It's just a slight variant of Shellsort. There really is just a slight difference in how it's written. I just found another algorithm here. You'll note that we got this kind of told divide by 3. This is a little bit lengthier. It's not doing all of these comparisons in the if statement. This is, I would say, more complicated coding to do basically the same thing. Whereas this is kind of writing it all out, but you're still basically doing the same thing. This kind of splits it up into 3 sections, puts whatever you need in the top section in that top section, whatever's in the middle, whatever's in the bottom. And then it goes through and sorts them at the end. So let's take a quick look at the Shellsort 2. You may understand this a little bit better as it doesn't have a lot of complicated things going on in here. So let's see, Shellsort 2, 10,000. Oh wait, did I call it Shellsort 2? I guess I kind of have to give it an array, don't I? There we go. So we run it, 3 milliseconds, okay. Run it again, 57 milliseconds. A million. Da 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 da. 4,489. So actually, the Shellsort million is faster than this variation of Shellsort. And probably the major reason for that is, even though they aren't doing completely the same thing, this is a variation of Shellsort that's splitting it into 3s. This probably splits it into more pieces, and you see it's got a lot more complex ifs and stuff happening inside these statements, whereas this has them kind of happening outside of it, and there's actually a couple of loops here. Whereas this one has, it still has 3 loops, but I would say this is going to be faster because, you know, it's going to split them up. I would say this splits it into 3, this splits it into 2, but maybe more so depending on the size of the array. As you can see, this is way faster though. But again, they're both sorting. It's just they're approaching it a little differently. Wish I had a video of the Shellsort too so we could see the difference, but they've taken it off the website, I'm afraid. It used to be here. So that leaves us one more thing to check here. And this is actually not a sort we're going to have to write. But if you go to the very top and import java util.arrays, we can use the built-in sort so you can kind of see and compare that. Java, as I mentioned before, has a sort that's built into Java. So to use it, once we've got that imported, you simply use arrays.sort. And if we wanted to print to make sure it's sorted, you know, we can check that. But I'm going to tell you it sorts. So let's take a look at that for 10,000, 100,000, and oop, a million, 10 million, why not? That bubble sort at 10 million would have taken a tremendous amount of time, by the way. If you think that 100,000 takes like 12 seconds, 10 million would have taken you 20, 30, 40 minutes maybe. Now, what the arrays.sort uses, if I remember correctly, I want to say it uses a variation of, let's back up, quicksort. We can double check that just to make sure, but Java what sort is arrays.sort. Here we go, arrays.sort. Let's see if we can find a quick answer. All right. We found code, but that's not what I'm looking for. Which sorting is used? There we go. Quicksort. It uses sort method, uses quicksort, insertion sort, and merge sort. Well, it uses all three. Wait. There you go. Why do they use four different types? Oh, it depends on what's happening. Uses quicksort for arrays of primitives and merge for arrays of objects. I believe that most of the time quicksort is faster than merge sort and costs less memory. According to this, quicksort's not stable, blah, 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 blah. Well, there's a little bit of information about when you're sorting different values, it is faster if it's like a 1, 2, 3 as opposed to you going in checking strings and objects and things like that. Uh, a lot of that stuff can, like, imagine playing a game where if you just decide to use this thing to sort everything, or this thing, you know, the difference in lag time in that game when it has to do that operation, your whole screen could freeze for a second or two, or not at all. It can have huge impact on your program itself. And that's where algorithms and doing things kind of efficiently comes into play. That's the point of the class, to learn how to do things in a way where you're just not draining resources from the machine, you're doing things as efficiently as you can. And that goes down to either the algorithms or how you're storing them, how you're accessing them. Actually, printing from a two-dimensional array, if you do it a certain way, it can be twice as fast or twice as slow if you do it another way. Depends on how you're going through that array. Perhaps we'll see a little example of that in the future. But anyway, that's your quick introduction into most of the loop sorts. Now the next sorts we go through will be the recursive sorts, which are these guys. And if I just do a quick show, you'll see that the code's quite a bit more complicated. The recursive sorts usually actually have multiple files, but in login time, login, these are significantly faster. Quicksort, in login most of the time, but could go to O2, which is why they say it's not completely stable. Depends on if it's one of these particular things, like few unique, I think, is the one that kills it. But there you go. Just a kind of brief overview of big O complexities and some of these sorting algorithms we're going through. But we'll see these merge and quick, maybe heap, we'll see in the future.